Okay, greetings, fellow bears, explorers. Today we're going to go over the Earth curvature and look at the math behind the 8 inches per mile squared.
Of the Earth curve, yeah.
Mm-hmm.
So just a rough derivation of that quick, and then kind of talking about why you can't just think about Earth curve when you're talking about how far you're seeing an object. So just to step through, I guess, the derivation for the Earth curve, what you're finding is your tangent line from your location and the drop from that tangent to the surface of the Earth being a sphere. 8 inches per mile squared is a parabolic equation. But if the Earth is a sphere, a parabola is only going to approximate a sphere or circle for so long. And you can see that in the derivation of the 8 inches per mile squared, which it assumes that for this distance here from your observer to your target, your D1, that's this whole triangle here, is approximately the same as your arc distance here along the Earth, because when calculating this arc distance, D1, is theta, this angle, times your radius. D1 is this triangle. So we can just find D1 by your tangent of theta is going to be your opposite over your adjacent. So that's D1 over R. But for a small theta, tangent theta equals theta. So we just get your delta 1 equaling theta R is the same as D1 equaling theta, because tangent theta equals theta R. So you're already making an approximation that for small angles, tangent theta equals theta. So this is only going to be an approximation for a given distance.
So SQB, why can we do that? Is it because the distance that we're measuring is inconsequential to the radius of the Earth?
Yeah, essentially yes. So a lot of times in engineering and in mathematics, there's the property of the small angle approximation, that a tangent theta equals theta for only a small angle. I think up to 0.01 or 2 radians, you're at 0.1% error. So given the radius of Earth, I think it comes out to about 200, 250 miles or so, you're going to be less than 0.1% error of your actual drop. So then you can calculate this drop distance by using this triangle, because if you know this height here, this is your drop. So drop is going to be your radius minus your radius cosine theta here. And then again, we're using the small angle approximation, and cosine theta equals 1 minus theta squared over 2. I mean, it's just a...
It's a simple algebraic substitution, the breakdown of the cosines.
Yeah. So then once you start subbing this stuff in, your 1 minus theta squared over 2 for your cosine theta here into your drop equation. We pull R through, and then we sub in our theta equals our D1 over R. We get our drop equaling D1 squared over 2 times your radius of your Earth. And then the radius of the Earth being on average 3959 miles, multiplied or converting that into inches, you get your 8 inches per mile squared. So again, this is an approximation because we're using 2 small angle approximations for trigonometric functions.
Essentially what the problem breaks down to is, one, like Squatting Bear said, we're using small angle theorem to approximate this distance, and 2, it's converting polar to Cartesian coordinates and vice versa, because most people understand the world as they see them in a Cartesian plane, which is like XY, which is flat. So So we went through, we derived the 8 inches per mile squared, which we're not disputing. You know, that's a good approximation. It's a good model up to a point. It's only a second order polynomial model, so that's why it drops off after a certain distance. So now, what Squatting Bear went through is that he actually pulled the data that Rowbotham used, and we went through it, and we were trying to, well, you go for it while I set up the computer over there.
Okay.
So,
And so, like I was saying before, this is your 8 inches per mile squared. That's the tangent line from your location, drop to your target location. This is not if you're able to see your target, because you have to take into account the height of your observation and the height of your target to see if it's going to crest over the, I guess, the circular cross-section of the Earth. And so that's kind of what this diagram is showing. So you have to take into your height into account and your observation height of the lighthouse. And so briefly, I did a quick just summarization. I found the book that Samuel Rowbotham was trying to use to discredit lighthouses and a spherical Earth.
why you could see a lighthouse for so far.
Right.
You know, if the Earth was a disk model, why can you see a lighthouse that far under a globe or under a sphere model? Excuse me. He was trying to prove that you couldn't see them.
Right.
So we're going to use his data that he measured out, or his data set, right? I think he took that from somebody else who measured it out.
Right.
Way back in
No, I
1800s.
used the book Lighthouses of the World that was printed in 1881. I found that copy, I think it was 1881, that copy of the book with the data right from it. And I just started doing a statistical analysis of all of it, comparing it to this model of the Earth, or not model, but taking into account the height of the observer, approximately 10 feet off the surface, because you're going to have the deck of your boat, and then you're going to have your observer height, and you have to take into account the height of the lighthouse. You can't just do your 8 inches per mile squared and say, oh, it's X amount of miles away, it should be 20,000 feet of curvature.
Well,
That's absurd, but
while I explain that, well, you want to log into the computer real quick?
Yeah.
Because you're logged into it. So what is essentially is going on here is light needs a direct path to your eye. You're not going to see anything unless you have a direct path, right? Regardless if that light refracts with whatever medium it's going to be in. So what we're doing in here is like the height at what you could visibly see, which is all this right here, right? Like you can see this light coming out of here from the lighthouse and the roof of the lighthouse, right? That's what you can see. You can't see this at all. That's what we're theorizing due to the sphere model. This is our hidden distance, and that's what we're going to show with the data set from 1836, was it?
right. Yeah.
Okay.
So now this calculation, not including refraction, not including anything like that, even though we did a brief test on seeing if we can even refract a laser over just a short distance. So this is just geometrical approximation, no refraction taken into account. Observer height of 10 feet, and the book had a distance for your height of your lighthouse. It
Assumed high tide.
It assumed high tide, so it was the
negate
smallest
any type of-
distance,
yeah.
the smallest height that your lighthouse could be. From high tide to the light of the lighthouse.
And you're getting the 10 feet from the book itself too, right?
Yeah, the book was also stating that the distance that you could see, the range of sight for these lighthouses was approximating a 10-foot high observer. So just using those numbers, straight geometrical approximation, no refraction, none of that. So far, I've plotted about 300 plus data points. If you want to
Yep.
go to the camera, I can just briefly show over here. About 300 plus data points analyzed from this book. And so I started filling out some of the names of the lighthouse over here.
Yep, so this is straight from the book, which is the name of the lighthouse, and then you got the height above the water, You want to get off that link.
Yeah. So
And then you have your
Sorry.
visible miles. That's all data from the book that we took from the book.
Yeah. So here's the book of the, let's see if I can go right to loading the first. It's hard to see in here, but lighthouses of the world. Oh, here's a description now. Lighthouses of the world, 1861, sorry.
Okay.
That copy of the book. And I just started going through some brief summarization of what lighthouses are and the types of lights used in lighthouses. And here's the general remarks. I wasn't. In here, I think it's talking about where. Okay, so height of the
Visible in
from
miles.
high tide level, visible in miles, 10 feet above the sea level, and then I just started plugging and chugging all of the data points for height above water and visible miles, and I just started plugging all of these in, gave in my 8 inches per mile squared number for the earth curve, and you have to account for the hidden distance. So once you account for hidden distance, I did just
And the hidden distance is stuff that we, it was just the height, the documented height of the lighthouse minus our projection based on a sphere model,
yeah,
right?
So here's a quick calculation of it. I can go through the derivation of the hidden target distance as well. And then whether it's seen or unseen. So of these 300 plus data points, about 303 data points, how many were not seen was, let's see here. 19 of these 303 are not seen because of Earth curve. Of those 19, I checked them again. 16 of them were plus or minus 30 feet or so within the Earth curve data. So, if you're off by maybe a mile or two in your actual observed distance, or if you have a crest of a wave, your boat is slightly higher, and you could climb up some of your, there's the mast or whatever of the ship, and be able to see slightly further. I think 30 feet is a reasonable assumption of that. And so only 3 then fall outside of just a normal Earth curve calculation. And of those 3, one of them I followed up on, and I know it for sure is a typo. So it gave a range of 60 miles, and it was really just 6. So of 300 data points, most of these are approximating the curvature of the Earth really closely. And so I'm not exactly sure if Rowbotham didn't assume the correct height of the observer versus the height of the lighthouse and take that into account and just did.
Well, what I'll do is, here. What I'll do is I'll actually go through and I'll run this through some advanced statistical analysis, and we'll see if any of these points are considered outliers, like way out there. Like
Couple standard deviations.
Yeah, with standard deviation, because one of them, he said that he had a visible distance of 60 miles, which is like 3 times the height of the frickin', it was an ungodly amount of the height of the lighthouse, which is like impossible. So, as Scotty Barter said, he did some investigation on it, found out that it's misplaced decimal point on the initial recording, so that happens. We're all human, we all make mistakes. So, but that's what we're gonna do, and you'll see that from us in the future. All right, guys, have fun, be good in the comments. We've got some people who have been very vile towards SQB and me just because we're going through the math. And that's the only thing that we're going through, right? So that's all we want to do.
Yeah, we're just trying to talk about the numbers here. Both of us think that the Earth is spherical. We're not trying to blast anyone. We're just talking about the math, going through the numbers, and analyzing it one way or the other. Statistically, it lines up with global math. Don't really see any massive outliers like we were saying, but we'll go through a finer tooth analysis of this stuff. So.
Yep. All right, guys, be safe.
Yep, see ya.